So in the past, we've already talked about light and different things that it does. We know how it behaves kind of as a particle in that it wants to knock electrons off of an electroscope when you increase its frequency. We also know that light, it behaves as a wave in that it diffracts and it interferes. So to kind of show this a little bit, we know that whenever we have a slit and we're spraying a wave through it, let's say water for right now, and this is our screen that we're detecting it on, we know that it's going to kind of bend around, right? Whenever it bends around, we're going to find the most intensity in the middle, and it's going to kind of gradually decrease its intensity out towards the outside. Okay? So that's diffraction. While if we have two slits and we're passing a wave through, we're going to see a different picture. You're going to have the wave that's diffracting on either side, and if you were to measure the intensities, you would see an interference pattern. We have the most intensity in the middle, and then some destructive interference on the sides, and then some more constructive interference, or some more intensity, more destructive interference, and then more intensity. So that's what waves do. What particles are supposed to do, kind of, what we're used to, is whenever we send particles through one slit, and let's say this is our cannon, or whatever, particles, whenever they go through, they're going to be stopped by the barriers, they're not going to diffract. Whenever we send them through two slits, say we were just shooting like an AK at it or whatever, this is our gun. If we're shooting that at two slits, we're just going to see two bands or two lines of bullet holes. So we see the difference between how waves behave and how particles behave. Now what happened, this guy, Louis de Broglie, he came up with this equation saying that particles, they actually have wave properties as well. And scientists, they had a hard time accepting this. They had a hard time like even giving him his PhD for this. And later on, they wound up doing some experiments to confirm this, this hypothesis. So this equation, it states that the wavelength, and that's what this weird letter means, lambda, it's wavelength, it's equal to Planck's constant over momentum, which you could write either as P or mv. So whenever you're looking at this, you have Planck's constant, which is a tiny number in the numerator, and you have a mass times the velocity, which for particles, it could be pretty big. Like if we're talking about a semi-truck, you have a pretty big mass. So whenever you're trying to measure a wavelength of tangible things like a semi-truck or something that's big, we have a huge mass, and we have a decent sized velocity that we have in the denominator, and a tiny number up top. That's going to give us a tiny, tiny wavelength where it's so small we can't even detect it. So they had a hard time doing experiments with these. But if we take really small things, like let's say photons or electrons, like the smallest things we could possibly get our hands on, and we put those in the denominator, they have virtually no mass, like as next to nothing as anything can get. Whenever you have a really small number here and a pretty small number up here too, the wavelength actually starts getting bigger. So it gets measurable. And they decided to do some experiments with electrons to see how they would behave. Now what it did, first off, it confirmed this equation. They wound up giving him his Nobel Prize for it. What else it did, it kind of opened the door for quantum physics. It's a bunch of weird stuff that happened, depending on whether or not you're observing it or not. So to kind of explain, they took electrons and they shot them through a single slit. Whenever they did this, they expected to see a single band of electrons just right behind, just like baseballs or just like bullets if you're shooting that through a single slit. What actually happened though, it started diffracting. So it did have its most intensity in the middle, just like the wave, but it did have electrons that kind of spread out. They thought maybe the electrons are bumping into each other, so they shot them one at a time, and it gave the same exact result. So it showed that electrons, they're actually diffracting. Those are particles that are diffracting, which is something that only waves do. They tried it again with two slits to see what would happen. Whenever they tried this, they thought there was no way that we're going to have wave behavior in this case. We should see just two bands. These are particles we're shooting through. They saw an interference pattern eventually over a long period of time. They tried it with a whole bunch of electrons. They tried it with one electron at a time. And every time they tried this experiment, it showed an interference pattern. And that's something that only waves do. So whenever they tried these things, it matched with the equation that de Broglie came up with. And they concluded like, hey, electrons actually do have a dual nature, kind of like photons do, or kind of like light does. And then they tried a few more experiments. Eventually they just concluded, what the heck, everything has a wavelength. Everything is both a wave and a particle. It's just whenever you get smaller and smaller and smaller, it's actually kind of easier to see things as waves than it is to see them as particles. Whenever you get bigger, it's like a semi-truck, for example, it's easier to see them as particles instead of waves. And it's just because whenever you get smaller, you can measure the wavelength a little bit better. So these experiments just confirm that. Now, to kind of branch away from what this equation is saying, they tried further experiments to figure out more about this weird behavior. And that's kind of whenever they open the door to the quantum physics, the stuff that really doesn't make sense. So they took, let's say, a double slit, and they wanted to peek at it to see which slit the electron was going through. So we'll say they stuck an observer here. I'm just going to draw it like a little eye. But they had a detector that could be able to observe what the electron was doing. Whenever they did that, and they shot the electrons through just like they did before, but all they did this time was actually peek at it to see what slit it was going through, it collapsed the wave behavior. And all they saw on the back screen was two slits. They tried this with all the electrons at once. They tried it with one electron at a time, and they had the same result every time that they were peeking at it. It was just two bands of bullet holes, we'll say. Whenever over here, if they took the observer away, it interfered. It showed wave properties. Now this is something that you guys don't have to understand why it does what it does. I don't even think the physicists know exactly why it does that. I know I don't. But you do have to know that it does. So a good practice would be take different scenarios where you have one slit, two slits, a bunch of electrons at a time, one electron at a time, and see what you're going to find on the back screen. If I have two slits like this, and I shoot one electron through without an observer, then where's that electron most likely going to be? It's most likely actually going to be right in the middle, not between or not behind either of these two slits. Now, if I stick an observer there, where's that electron probably going to be? At that point, it's impossible for it to be right in the middle because it's not behaving as a wave. Think whenever you have an observer looking at the slits, it's behaving as a particle. So you're going to see it behind either one of those slits, one or the other, but not anywhere else. Okay? So it's good to kind of practice what images you're going to get whenever you have one electron, a bunch of electrons, observer, no observer. Okay? Anyway, another thing I wanted to talk about, and this is another weird thing that they were able to conclude, this is called Heisenberg's uncertainty principle. What it states is that you can only know so much whenever you're looking at quantum stuff. Whenever I say quantum, I mean tiny, tiny, tiny things. So you can only know so much about the behavior of electrons or photons or things like that. It says that the measurement of, and this is a measurement of uncertainty, it's not a measurement of how much we know, it's a measurement of how much we don't know. So the measurement of uncertainty of momentum times the measurement of uncertainty of position has to be greater than or equal to some number that's actually close to Planck's constant. Okay? So this is saying we have only so much that we're allowed to know in a sense. So if we know a whole lot about the position of an electron, we don't know much about its momentum. If we know a whole lot about its momentum, or in other words, where it's going, we don't know much about the position of the electron. And this doesn't make a whole lot of sense whenever you're talking about particles. But if you're thinking about waves, it kind of does. So let's think about waves, for example. If I have water that's trying to pass through a wide slit like this, then what happens is it's not going to diffract so much if the slit's wide. You have to have a slit that's close to the wavelength. So here we don't know much about its position, but we have a pretty good idea of its momentum or where it's going. While if we have a thin slit, if it's a slit that's close to the wavelength of the water or whatever you're passing through it, if it's a thin slit, we know a lot about its position, but it's going to diffract. And I mean, we have a hard time saying where it's going. So this is what we call Heisenberg's uncertainty principle. Now, it can be used whenever we're talking about electrons. That's actually whenever he came up with it. If we're shooting electrons through a wide slit, we don't know much about where the electron is, but we have a pretty good idea of where it's going. Now, if we narrow the slit and we're shooting electrons through, the electrons are going to diffract. We have a pretty good idea about where the electron is, but we know less about where it's going. So if I was to shoot one electron through a wide slit, I have a better idea of where that electron is going than I do in this situation. So over here, the electron is going to be somewhere in these boundaries, probably right there. Okay? While over here, if I shoot one electron through, I have a good idea where the electron is, but less about where it's going. It could be here, or anywhere within that diffraction pattern. So that in a nutshell is what Heisenberg's uncertainty principle states. Now what this does, it opens the door for the quantum model of the atom. And this eventually is kind of what resolved the problems with Bohr's model of the atom.